So funnily enough, Veritasium, which is a very popular physics and science channel on YouTube, just published a very nice video on the history of complex numbers. And it ended with a little segment on how complex numbers are used in Schrodinger equation. So it has a little bit of an overlap with what we talked about in last class. So I was watching this late last night when I posted it on the Slack channel. Please have a look, okay? So last time we wrote down the central equation for non-relativistic quantum mechanics, the Schrodinger wave equation. So let me remind you what it looks like. It's an equation, it's a complex equation. I h bar d psi by dt is equal to minus h squared by 2m del squared, which is the Laplacian, psi plus the potential psi. Okay, so for now, so psi is a complex wave function, and it is a function of space and time. So it's called the wave function. Which is, for now, it is a function of space and time, is a complex function, okay? So in future, we'll see that it may have more degrees of freedom depending on if the particle we're describing has spin or some other internal quantum number. Okay, so what is this wave function? Of course, this is a wave function that de Broglie talked about, but de Broglie was not able to give a very explicit equation for it, at least not in the way that we understand it now. So let's just see what this wave function is about. So first of all, unlike classical waves, psi is, in general, complex. Okay, so that's something I just want to emphasize a lot. It doesn't always have to be complex, but for example, in the case of a bound state with definite energy, you can show that psi is actually not necessarily a complex function, but in general, it's a complex function. Okay? So it's a function of space and time coordinates. So according to the standard definition or standard formulation of quantum mechanics, okay, so if you hear a purring, that's my cat. He is trying to be part of the action. According to the he likes quantum mechanics, unlike Schrodinger's cat. According to the standard formulation of quantum mechanics, a wave function contains all the information that may be known about a system. Because of this, often the wave function is called the state of the system. Or it's called the state vector. And you might say, why is it a vector? Why do we use the word vector? Because you can think of functions as generalized vectors, vectors in an infinite dimensional vector space. And when the time comes, we will explore that interpretation. Okay. For now, just think of the wave function as a function, which is the state, which gives you the state of the system. So another thing we assume now, but it's not necessary, okay, not another thing, one thing that we assume for this course assume here is that the potential is independent of time. It doesn't have to be. If it's not independent of time, then we have to, solving the Schrodinger equation becomes harder. But even that can be done, and that was the general solution. The general formal solution to time-dependent Hamiltonian was given by Freeman-Dyson. So the general formal solution to time-dependent, time-dependent V of xt was given by Freeman-Dyson, and it's known as the Dyson series. I had the great pleasure and opportunity to meet Freeman-Dyson a few years before he died, and I spent 2 days talking to him. At some point, I'll publish those videos. All right, so anyway, this is not something we will be bothered about. For us, the potential will be time independent, okay? So the interpretation of the wave function was given by Max Born. And the interpretation was given in a famous paper by Max Born, but the interpretation was in a footnote. Okay. So in a footnote, Max Born, what did he say? He said that psi gives us the probability density in the following way. Psi is a complex number, so how can we get probability out of a complex numbers? Well, we have to take some sort of real version of it, right? So the probability, it can be the absolute probability or the relative probability of finding a quantum particle in the interval, say d cubed x, around the point x at time t is given by the probability density, which is a function of x and t, times d cubed of x, the volume element. And this is given by psi star x of t times psi of x of t times d cubed of x, or the modulus of psi t squared d cubed of x, okay? So this is what gives the probability, relative or absolute. Okay, is that clear? At least formally what I'm saying?
This probability density is in a volume independent of time, but the P has time as an argument.
Yeah, P has the time as an argument because psi in general has time as argument, right? So, if the particle is moving, then that probability density is going to change, right? That probability is going to change, right? So, for example, if I look at a small volume of space, and this is, say, the wave function, and it's moving, say, in this direction with some velocity. Sorry. Yeah, my cat did it.
This is like beginning of a rap song.
Yeah, it's just like he came up and he just started napping on my keyboard, and it started some weird. It just yeah. Anyway, can you hear
Infinite
me now?
feedback.
Yeah, positive feedback. Yeah. Okay, so if the if v is moving with a certain velocity v, then before the wave function goes through this volume, the probability will be 0, right? But when it's actually crossing it, the probability will be non-zero. So we can easily think of situations where the probability of finding a particle in a given volume is time dependent. Okay.
Okay, got it.
Okay, good. So this is the Born interpretation. And the Born interpretation is one of the postulates of quantum mechanics. So again, it's like the Schrodinger equation. We don't know why it works, but it works.